So this is number 10 on your cumulative review for today. All right. So consider an object moving on the line y equals 2x such that its projection on the x-axis is moving at 3 centimeters per second. If an observer at 4, 0 is watching the object through a telescope, at what rate will the telescope be rotating when the object's x position is 8? So there's a couple of key words here. Rate tells us it's a related rates problem. And rotating tells us specifically we are looking for a change in angle with respect to time. Okay, those keywords tell us a lot, believe it or not. So now we've got to figure out everything else dealing with this problem. So we have an object moving along a line y equals 2x. So I have a graph right here because I don't know about you guys, but it helps me to see kind of what's going on. So let's graph y equals 2x. So I'm going to make my x scale 1. And you guys, I'm going to do 3, 4, 5, 6, 7, 8. On my y, I'm going to make it 2. So 2, 4, 6, 8, 10. That way I just go up 1, I'll go 1 each time. Okay, so when x is 1, y is 2. When x is 2, y is 4, 3, 6, and so on. So I know I have this nice linear function. All right? So we got this particle moving along there, and we have a guy at a point 4, 0. He's got a telescope right here. Right? And so he's watching this particle move along this straight line. Maybe it's a satellite, or who knows what. It's moving along this straight line. And so the question is, when the particle has an x value of 8, so 1, 2, 3, 4, 5, 6, 7, 8, which notice its y value would then be up here. The question is, how fast is his angle changing? Okay? Now to work this, anytime we're working with angles, we want to somehow make a right triangle. So there's our theta. Okay, so we got this telescope that's tracking this object, and the question is, how fast is this angle changing in a given period of time? Now, let's see here. Let's try to calculate or catalog our variables here. So remember, we usually make the columns, the two columns we have constant and changing. All right, so constant versus change. Okay, so let's see here. Well, we have an angle. Is the angle constant or changing? The angle's changing. Okay. Let's see here. We have an x value. Is the x value constant or changing? X is also changing. At this instant, what is the x value? At this instant right here, when we're concerned with, x is 8. Okay. Is the rate of x changing? No. So dx dt is a constant of 3. This is the take-home quiz. Or take-home quiz. This is the review. Let's see here. What else do we have? What are the variables? We got a y. Is y constant or changing? If it's traveling along here, is y constant? Y is changing also. At this instant, what is y? This instant right here, it'd be 16. What about the rate of y? Well, y depends on the x value, doesn't it? So dy dt would be the derivative with respect to time of y, of 2x, which is 2 times the derivative of x, so 2 dx dt. Do we know dx dt? 3. So we have 2 times 3. So dy dt is 6. Okay? And then what we're looking for, remember, is d theta dt. Now, do we know anything specific about this angle measure at this instant? In other words, could I say that's 68 degrees? Or, 0.743 radians? Can I say that without any problem? No. So what we can do is, since we have a right triangle, we can use the trig ratio. Now, this side right here, how long is this side? Well, this is, it's 4, right? But what about when the particle was like right here? Right, then it was 2. So in terms of x, what is this distance? So like when x is 8, what is this length? Right here, what is this length? From our guy to 8, 4. When x was 6, what was the distance? 2. So in terms of x, like if x is 1,000,000, how do I find this distance? Subtract 4. So x minus 4. What is this distance? This one right here. Well, it's 16 right here, but what was it here? It was 8 here. So what's determining? What is this length always? It's defined as this. Right, that's the y value. You guys are overcomplicating it. Overthinking. Okay. So you guys okay with this is y, this is x minus 4. So what trig ratio do we have that'll help us find theta in terms of these two sides? Again? Good. Opposite over adjacent. Right? So tan theta equals y over x minus 4. Okay. So we find our derivative. So what's the derivative of tan theta? Secant squared theta d theta dt. And then to find the derivative of y over x minus 4, what rule do we have to use? We have to use the quotient rule. We move both these down. So let's see here. Low, so we have x minus 4 times the derivative of y, which would be dy dt, minus id low, so y. The derivative of x minus 4 would be dx dt. Remember, we're finding the derivative with respect to time here, not with respect to x. And this is all over x minus 4 squared. Okay. So let's go through. Do we have a value for x? Looking at our stuff up here. We have a value for x. We have a value for dy dt. We have a value for y. We have a value for dx dt. Okay. So do we know everything in this whole equation? Do we know d theta dt? Should we know it at this point? That's what we're looking for. So the answer, no, not really. Do we have a value for secant squared theta? No. So we need to figure out a value for secant squared theta. So what is secant theta? What is the identity for secant theta in terms of our right triangle? Not everyone at once. Well, related to something that you do know. What is secant related to? Sine or cosine? Reciprocal cosine. So what is cosine in terms of the right triangle? Which two sides? What's the ratio? For cosine? For cosine? So is it adjacent or opposite? That's a kind of a big deal. Adjacent? Okay. So then what would secant be? Hypotenuse over adjacent. Now at this instant, do we know the length of the adjacent side to our angle? How long is this side? Yeah, but at this instant, when x is 8, do we have a value? It's 4. Okay. Do we have a length for our hypotenuse at this instant? No, but we can find it using our good old Pythagorean theorem, right? So this is just a hypotenuse. So we have 4 and 16. So the hypotenuse will be the square root of 4 squared plus 16 squared. So 16 plus 256 is 272. Right? And so secant of theta will be the square root of 272 divided by the adjacent side, which the adjacent side here was 4. So we now have a value we can plug in for secant theta, because we have secant theta squared. Right? So we can square this. So we have the square root of 272 over 4 squared d theta dt equals, what was x? So 8 minus 4, dy dt was 6, minus y was 16, and dx dt was 3, over 8 minus 4 squared. So I keep this in exact form because, notice, we're going to square it right away anyway. All right, so when I square a square root, it goes away. So we've got 272 over 16 equal, d theta dt equals, and we got 4 times 6, that'd be 24, minus 16 times 3 is 48, divided by 4 squared, 16. And so we get negative 3/2. And 272 divided by 16, believe it or not, is 17. So 17 d theta dt equals negative 3/2. So d theta dt, or the rate of change of our angle, would be negative 3 over 34 radians per second. Okay. So again, when you see rate, that means it's relative rate. If you see rotation, that means you have to set some kind of trig function up. Very, 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 very often it is tangent. Okay? And most problems that I see are tangent. I won't say every problem, but most of them are tangent because the opposite and the adjacent are usually known values because they're x's and y's lots of times. Okay? So keep this tan theta equals the y value over the x value in mind whenever you see a problem that talks about a rate of change of an angle. Okay? All right. So make sure your names are on those reviews. I'm going to take those up. I'll check them and get them back to you this period. Don't worry. So far, the best I've seen is a 60. So let's see if we can. Better. Not optimistic, but it's okay. And forward. They're good problems. I think that it's not 80, but that doesn't count. Goes on. You mean 80? Yeah, there's 2 of them. Well, I didn't sit down. Sir? It's just a 0. Okay. Integration using the chain rule. Now, these problems are not too difficult if you've got the chain rule mastered. If you don't have the chain rule mastered, believe it or not, these problems will help you a whole lot with the chain rule. In other words, after doing a lot of these problems, you'll be going back to derivatives and it'll just be like second nature. Okay, this really reinforces the concept of the chain rule. So it says, consider using the chain rule and taking the derivative of f of x equals sine of 3x. So what is the derivative of sine of 3x? Well, we say the derivative of sine of the something is cosine of that thing, and we multiply by the derivative of the inside, right? So we have 3 times cosine 3x. Now I use u a lot, right? I just call it the u because it's just a variable I can refer to. So notice we've got the 3x inside. I'll call that u, right? And then we've got the u prime outside. Okay? So if we were going to go backwards through this process, the key is we need a u prime outside and a u inside, and then we can integrate this just as if it were cosine of x. Okay, or in this case, cosine of u. Okay? So let's look at a quick example. We have 3 cosine 3x. So the inside here, I'm going to call this our u. Now what would be the derivative of 3x? 3. So there is our u prime. So notice we have cosine of u and u prime. So the integral of cosine of u and u prime becomes Well, what's the integral of cosine? Sine of u plus c. Now think about this for a second. Again, if we take the derivative of sine of 3x using the chain rule, the derivative of sine is cosine, the inside stays the same, and we multiply by the derivative. So when we integrate, we need the derivative of the inside there. And then when we integrate, it goes away. Okay, we're kind of thinking backwards here. Okay? So let's do another example. Let's start off by, we have a square root. How do we want to rewrite this? Rewrite square roots as fractional. So 4 times 4x plus 2 to the 1/2 dx. Now, what is the, I'll call it u here. What is the inside? 4x plus 2. So this is our u. What is u prime? What is the derivative of 4x plus 2? 4. So we've got the u prime. So we can think of this as if it were just the integral of u to the 1/2. Okay? And so the integral of u to the 1/2 would give us u, so that same thing, 4x plus 2 to the what power? We add 1. Remember, we add 1 to the exponent, so 3/2. We divide by that same exponent. Put plus c. So we're divided by 3/2, so that's the same as 2/3 times 4x plus 2 to the 3/2 plus c. Okay, now, again, to convince yourself that this works, it's not a matter of exactly understanding right now exactly how all this stuff works. You need to convince yourself that it works. So if we take the derivative of this, we would multiply the exponent times 2/3. So what is 3/2 times 2/3? Are we okay with that being 1? Okay. Convince yourself that that is 1. We subtract 1 from the exponent, so what's the new exponent? 1/2. And we multiply by the derivative of 4x plus 2, which is where we get this 4 from. Okay, so if we find the derivative of this, the power and this coefficient, they cancel out, right? And we're left with that derivative out here. So it works. Next example. Let's start off again, rewrite it as a fractional exponent. So 22x, 11x squared minus 5. And the cubed root, remember, is the 1/3 power. 4th root would be 1/4, 5th root 1/5, and so on. So what is the u here, so to speak? What's the inside? Okay. What is u prime? Isn't that convenient? So we have something raised to the 1/3, and we have the derivative of that something. So we can use the chain rule in reverse. So we add 1 to the exponent. So we have 11x squared minus 5. Notice that doesn't change. Add 1 to our exponent. So that's 4/3. And that's over 4/3 plus c. So we get 3/4, 11x squared minus 5 to the 4/3 plus c. And again, just convincing yourself that this works, multiply 4/3 times 3/4, that gives us 1. We would take away 1 from the exponent, so there's our 1/3 power, and the derivative of the inside is 22x. That's where that's coming from. Okay. So notice on all these, the u prime has been there, nice and clear, right? So when u prime is there, you just imagine it's not, and you integrate the rest of the part, the rest of the integrand. But what if the u prime isn't there? So it says consider the integral of sine of 4x dx. Now what would be the u here? The 4x. And what would be u prime? 4, but there isn't a 4. So we've got a bit of a problem. Okay? Because when we do the chain rule, we're going to have a 4 hanging out. We've got to get rid of that 4. And so the general idea here is we multiply by 1. But not just any 1. We multiply by whatever 1 is convenient. In this case, we're going to multiply by essentially 4 over 4, or 1/4 times 4. Let's do this example. So the integral of sine of 4x. Now, again, I recognize that this is my u. I'm missing a u prime. So what I do is I say, well, I want a 4. This is really what I want to say. I want 4 sine of 4x dx. But I can't just willy-nilly multiply by anything I want. I can only multiply by 1. So what else do I need to multiply by to make this 1? Multiply by 1/4. Now notice, this is a constant. So conveniently, I can pull it out of the integral and imagine that it's just being factored out. So we have 1/4 times the integral of 4 sine of 4x. And now we've got our u and our u prime. And so now this is just like sine of something. The integral of sine of something, well, it would be negative cosine, that same thing. So I've got negative cosine 4x. Now again, convincing yourself that this works is really, really important. You really have to convince yourself that it will always work. Think about it this way. The derivative of cosine would give us negative sine, which is why this negative cancels out. The derivative of the 4x, that would give us that extra 4. 4 times 1/4 is 1. So that's why we don't have any kind of coefficient. Okay. Now, here's a little warning. Notice how all of our u primes so far have either been there, or in this case, it wasn't there, but it was a constant. If our u prime isn't there, but includes an x, like here we have 4x squared, what would u prime be? It would be 8x. Right? It seems like we ought to be able to multiply by like 8x over 8x and factor out 1 over 8x. Okay? The problem is we can't pull an x out of an integral, only constants. So this doesn't work. Okay? That's what it says. Variables cannot migrate across integral signs like constants can. So here I pulled this 1/4 out. You can't do that if there's an x there. So if you get a problem like this, where your u prime includes a variable, and it's not there, it's entirely possible the integral can't be done. And in fact, right now, at this point, there's quite a few that we just have to say we can't do it yet. Okay? So whenever you're working the assignment, keep that in mind. If you get to a problem, and it can't be done, just write that. It can't be done. Okay? Questions or concerns on these so far? All right, you got the remainder of the period. Ask questions when you got them.